Okay, so hello everyone. Um, this is the group of Dungog, presenting an NFA transition with NFA automata with MC transition, wherein the NFA is then converted to PFA. So here's the program. First, what we have here is just a static NFA. Here you can see the state and where those states with specific characters leads to. For example, if you are in Q0 and then B is the Q1, Q1. Now this would be an empty string. This represents the epsilon transition. Basically, here it is a movement without consuming input. Basically, this is like a free pass from Q1 to Q2 without reading any input from the language or string that is given. So and then if you're in Q2, A is to Q2 and Q3, B is only Q2, Q3, going to Q4, and Q4 is the accepting state. So you can see here, alphabet, start state, and accept state. So now, first of all, what is this? No, what is, we're going to explain each method, how it works. So in this line of snippet of code, this iterates over each state and its transition. Basically, in NFA, as I have identified before, the state Q0, Q2, to Q4, this will iterate over that static NFA and checks if the symbol is an empty string. That will be, that will be an excellent transition or empty transition. And the targets, the targets here, um, the the targets here indicates uh, the next state in which the NFA transition of a specific symbol is going to be. Basically, the targets are like, for example, you have a symbol B. What is the target of symbol B? If you are on this state, basically it's like the next state, but you know, it's it's kind of the same. And then this is printed, you know, as a transition table. Um, yeah, transition table to show the transition of each iteration of step, or validation of the string. Now, for this one, here is to print the five tuple of the NFA. So, although it prints out the transition table that is separate, I mean, they're still the same, but I have another printing of sort of the five tuples, specifically each iteration of each, you know. Now, what we have here is that first it prints out the state, the state, it joins all the states, the alphabet, that, and here is the start of a transition function. Um, for state in state, for every state in the state, um, enter symbols and targets in the NFA state. If the symbol is E or like this, then basically this means uh, it's a free pass, free pass, you know. It's like Q2, if you find this on Q2, go directly to Q3, you know. Um, and then start state, just print out start state and print out the, the shifting state. Okay, next one is here, epsilon-closure. Basically, um it computes all the states that can be reached from a given state using empty transition. Basically, it's like mapping the state and the transition from a given state using only empty transition. Here it starts with the, like the state, you know, it starts with a given state here. And using stock, you know, or easier DFS traversal. So we could, like, we just pop and pop. And while this is true, while well, I mean, there is this after initializing the given state, you know, and then after performing a DFS, to explore all empty reachable states, and putting it in a path, this loop will continue. As you can see here, it's a while loop. This will continue up until there are no more states to process. Basically, it will iterate through every state using an anticipation, and then it will continue up until there are no more states to process. Current here is the current state that is being explored at the moment. So um, this for this one just get that basically means that it just gets the transition that gets the current, you know, it gets the transition. Here, the second one, it fetches the empty transition naman niya. While the first one gets, the transition, let's say A to B, Q1, 0 to Q1, B, Q1, B, B0, like that. And then this one now gets the empty transition. No? Um, and then, if no empty transition exists, then uh, an empty set will be returned. If there's no value. There's an empty set. Um, and then here, if like we haven't visited, the next state, since if next state is not enclosure, if you haven't visited the next state, then add it to the closure set. Since we are iterating it from the start state, so basically we are starting from scratch, basically building it again. So if we haven't already visited this, then add it to the closure, you know, and again push it to the state. So we can see the um, transition in the next iteration, you know. So and then after that, we just return the closure to be used later on. Um, so, defining. Okay, so step five. Now we are going to simulate the NFA of an input string, and basically this is like again the uh, NFA table where if ever we have an input string, let's say we have a string BBA, BA, BA, like this. Now, by the way, uh, this one, This only accepts languages that start with B and ends with AB. So it's like this. So what happens here, since a static NFA will always have the same five tuples, we are going to create a transition table based on the inputted string itself. So this is what this is, you know. It creates an NFA based on the inputted symbol. Yeah. Step by step. First, here is we start with the here. But here before consuming input. Basically, this is empty transition. Yeah, that's the basically it's, an enclosure on the first state. First is in step zero. First step kaya step zero. Different you know before input is processed. And then here you can see we have an iteration for loop where for each input symbol we get all the transitions from the current state. Um, we take the empty closure of all the floating states and then update and print, you know, the update and print the current state. Uh, you know, um, the current state is where you're at right now. So we check in the end whether the current state, if any current state, is in the set of accepted state. You will see later on it is. And then here it says yes if it is accepted and no if it is not based on the language provided by the static NFA. Um, here for convert after the acceptance of the inputted string to a DSA from an NFA. If accepted, we are going to convert it into a DSA. So how do we do that? Well, first of all, we have to remove the entry transition from the NFA since in the DSA there is no entry transition. And then state for state. Basically, we are going to focus state by state of the DSA based on the DSA based on the NFS. First, what we do here is yeah, we compute all the closures first, and then we create a new uh, NFA basically. Where we check here, basically here this one is checking. Where for each symbol we expand all the transitions via e-closure, and if the result is an equivalent NFA, and basically this ends with again this ends with a result where A and B characters are you know they're the only characters in it. Basically, we are creating this NFA from scratch again to remove the entity system so that what would remain is A and B. And again, we make sure that we handle the passing of each possible character or input. Oh yes, each possible character in the alphabet to be managed. For example, there should be A and B for each state, since that is the role of the DSA. So we make sure of that. Okay. And then here is the Again, the annotated DFA such construction. So what we use here is the subset construction algorithm. What we do first is to what from the new initialized NFA that we did, that we created, we start from the here, from the start state, where each set of NFA states will be treated as a single DFA state. Basically, state by state will be treated just like how we convert NFA to DFA on a piece of paper. Each state of an NFA must to have an equivalent DFA state. So basically, that this is what it means. And then we start with D0. We just start at D0. Um, and then for this while Q, while loop, this basically just iterates over each state. You know, it just iterates over each state, and then it computes this one. It computes the set of NFA states that is reachable by the symbol. For example, we have a symbol A, then we have to compute the set of NFA states where this is reachable based on the symbol. Let's say A. Yeah. And then um, uh, here. Okay. So if not in next step, this means that if this state, the DFA state, doesn't exist yet, again, since we are starting from scratch from 2-0, state by state, if this doesn't exist yet, then we assign it a name and save it. You know, so we are starting from D0, so we are going to use the same naming convention. So D0, D1, D2, D3, and so on and so forth. After adding the state, we link, you know, here, after having here, next name, after naming the state, what we do is we link that state to a new one, you know, the current state to a new one, the new DFA state that we have just named, using a symbol based on what symbol we are at right now. And if any state in this DFA is like accepting, mark the DFA state as accepting. Basically, that's how we know which is the accepting state in the DFA. No, we base it on the accepting state of the NFA. That's how we know which uh, state is the accepting state in the DFA. And then we move to printing. So this is just basically printing the five tuples of the DFA, just like how or what we did here. Here, yeah, bringing the five tuples. And lastly is the main. This is where everything is um integrate. I'm Yeah. Actually, this is the all of them collide, all the different methods, because this prints the NFA first. Basically, what to give you a quick summary. This would print the NFA, you know, the the five tuples of the static NFA. It would then get user input. The user input would be a string, and it would check if that string is accepted or not based on the language where character B should start and AB should end. Then it simulates the NFA. It simulates the NFA based on that inputted string. It will then send or print. Um, it will call the method where we print the NFA transition based on inputted symbols. Input yes, based on inputted um, value. And then if accepted, it will then convert the NFA to the FA. So like this. First here is to display the transition table of the static NFA. And then you need to restrict it because um, we have to iterate over each symbol one by one. So if we aren't going to strip it, it will take the whole input as a whole, like this, instead of having the like this separated. I mean, not separated by a white space, but separated as a whole in general. Now here we simulate NFA state step by step. Uh, we call the simulate NFA with table method, preparing without the transition, converting the NFA to DFA if it has been cleaned by epsilon, print the DFA transition table as well as the five tuples of the DFA, print the start, print accept. Here is the five tuples, or else reject. So, okay, let's look at this, look how it works. Okay, so first, what we have here, the transition table of the NFA, the static NFA. This is before we create an NFA based on an inputted symbol. So Q0 to Q1 is connected by B, Q1 to Q2 by epsilon or resistance. Q2 has a loop on itself with the symbol A, and it also connects to Q3. Q2 also has B to itself, so meaning AB goes to Q2 itself, and Q3 to B. Q3 is connected by B to Q4. So here are the states, here are the alphabet, five tuples, where the initial state is Q0 and the final state is Q4. Now let's input a string. What if we input a string that is not accepted by the language? Since what this NFA accepts is character or strings that start with characters B and ends with AB. So let's say we have A. As you can see, it will try to simulate the NFA table, you know, but it won't even be able to move past step one, as since step zero here will always be empty. It will always be epsilon, so it will always um, point back to the initial state. So before it even began, splitting its input string one by one, it it says no, because this doesn't fit the language of the NFA we have. So, ah, so let's say BA, BB. Now this should be accepted. Enter. Ah, wait, okay. Okay. BA, BB, BA. This should be accepted. Enter. Okay. So again, what we have seen. So this is the first transition table before the input string, and now this is the transition table. You can see the first will always be epsilon, and this is the movement of the of its symbol on the current state. We'll check if it's accepted. It is accepted because on the last input there is Q4 here. So if any state is in the accepting state, after where in the last, you know, part na ng string, then that is accepted. As long as it, you know, it starts with B and then with A. You can also create a transition table first of the NFA based on the DFA based on the NFA. As you can see here, for every letter BA, 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 it will be accommodated. Starts at 0, accept state is B4, quadruple. Basically, this is um, the movement of the input. You know, basically, this is what we use. I mean, you could graph this out when you write it, but I believe if you understand a transition table, you would understand how this looks like or what this looks like already. So, yeah, and yeah. So that was it again. We have transition table of the static NFA, same as with its quadruple. We input a string, it accepts only characters that starts with B and ends with AB. If it isn't the same with the language, then it is rejected. If it is the same, then it is accepted. That accepted input string will then create a new NFA where it is being simulated, where we print the simulation table on the transition table, you know, and then that the input string will then be converted to the DFA. The new NFA will be converted to the DFA. So this will be the transition table, start state, accept state, the five tuples, and yeah. So that's it. So thank you. That is our presentation of an NFA with epsilon transition, which converts it which which text a string based on a given set of rules, and then if accepted, it will be converted to a DFA. Thank you.